Hey everybody, welcome to the Geo-Files. Today's episode's a little special. As most of you know, I went in May to the Institute on Lake Superior Geology's 2018 meeting, 64th annual meeting, and they brought up something good that got me thinking. In that meeting, when we went on our field trips, it was shown to us how scientific knowledge can advance and change. And that's key to science. I'm going to get into the details in a little bit, but just first I want to explain something. Science changes to fit the data. That's the whole point. It's not a rigid thing. If your concept or your model is based on information at the time, that's good, but it could be totally wrong. As new information comes about, you change your model and your concept to fit the data. You don't change the data to fit your concept. Anyone who does that is not doing science, despite what they tell you. All right? That's not how you do science. That's how you do wishful thinking. All right? But that aside, all right, so I went on this meeting and something got me thinking. One of the field trips in the guidebook, they visited something called the Dickinson Group. I did not go on this field trip, but fortunately in the field trip guidebook, there's detailed information about it. All right, so I started reading it and it got me thinking about how we adapt our views to fit the data, and that changes over time. And this is a perfect real world example of how that happens in geology. All right, well, what you see here is a map. It's an excerpt from that trip field book here, and what you see here is something called a porphyritic red granite. Just keep that in your head for now because it's going to come up again later. And everything, all the slides are referenced here within. Anything I refer to later that isn't in a slide will be in a slide at the end and after the in the references. All right, what you're looking at here is a cross-section of how we presently think the Dickinson Group relates to surrounding formations. The Dickinson Group is now considered to be equivalent to the Menominee Group. It wasn't always that way, though. The pioneer and the guy that originally defined the Dickinson Group, a group in geology and stratigraphy is a formalized assemblage of formations. You don't have to put formations into a group, but if they're stratigraphically unique and distinct, you can do so. And that's what James did and everyone else in 1961. All right? But things were a little different then. Okay? It wasn't like it is now with radiometric dating. What I'm going to do before I start talking more about radiometric dating is I'm going to show you also from an abstract in the ILSG 2018 trip, that red granite has a firm date now. It's actually been dated to 2,099 million years, which is 2.099 million years, or if you were to round up, 2.1 billion. And the thing with these dates now is you don't usually see plus or minuses on them anymore for things in the Precambrian, because the technique has gotten so good that the margin of error is usually less than 0.1%. So when you're dealing with thousands of millions of years, being off of 1 or 2 million years doesn't matter. I'm going to talk a little bit here about radiometric dating. I'm not going to give you a whole background, I'm not getting technical stuff, I'm just going to give you a brief history. When James wrote this paper in 1961, radiometric dating had been around for a little over 55 years. 1907, Bertrand Boltwood was the first to actually radiometrically date rocks. All right. The mass spectrometer was invented in the 40s, kind of perfected-ish in the 50s. So as you can see, James is right around this transition from, dating things the best we can to getting very accurate numbers. Okay. So, but he was still kind of in the tail end or at the very, very beginning of that. Up until radiometric dating and up until right before James' time, there were still a lot of geologists that thought the Precambrian, before the Phanerozoic, before the Cambrian, Precambrian, that may have been represent a long period of time equal to the Phanerozoic, which would be from the base of the Cambrian to present day. When in actuality, the Precambrian is about 88.1% of Earth's history. But he didn't know that then, and Claire Patterson in 1956 was the first person to attempt to get an age of the Earth through radiometric dating. Radiometric dating had been done on rocks before that, but it just told you the age of those rocks. He came up with a method involving meteorites to get the age of the Earth, and that age hasn't changed very much since his 1956 result. All right, but 1956 is just 5 years before 1961, and James and everybody, when they defined the Dickinson group, all right, he divided the Precambrian into the lower, middle, and upper Precambrian. All right, words like Proterozoic and Archean were around then, but there was no North American stratigraphic code. There was no geologic consensus of a time scale. So a lot of these terms were used in different ways, some over here, some over there, just applying to different things. Although James also referred to something called the Algoma or Algoma granite. Actually, that's still used in Ontario to this day, basically for any Archean plutonic rock is what we use it for. It's been abandoned subsequently in the United States. But James referred to the lower Precambrian, which would be equivalent to the Archean, and he actually does say that. I'll get into it here in a minute. He doesn't really say that the middle Precambrian, what that equates to, but just from reading the way he's writing and the diabases and the dikes later in the paper, the middle Precambrian seems to refer to the Paleoproterozoic and Mesoproterozoic, and the upper Cambrian would refer to the Neoproterozoic. That's just the gist of what I could get from from the writing of that paper. So this is the present accepted GSA time scale. It was done in 2012, and here I divided out how James' concept was, but he had no idea the complexity that was herein, because this was all still new. All right, we didn't get the first consensus of it on a geologic timescale, I think, until 1983. So it would still be a few decades later. And he does use the word, like I said, Archean, his 1961 paper, which he does right after that equate to the lower Precambrian. So we do know he thought the Dickinson group was Archean, but I showed you earlier that we think it's equivalent to the Menominee group, which we know is not Archean. Well, how do we know that? Well, this is a slide from a publication that I updated actually a day or so before I was doing this video. And here we have a lot of detrital zircons from a lot of these formations in the Menominee and Marquette range. But remember, detrital zircons in sedimentary rocks can only give you a maximum age for the formation. You cannot be older than your youngest zircon if you're a sedimentary rock. All right, so that with the coupling of the dating of this granite now brings in the whole question, well, maybe the Dickinson group is a lot younger. And the second half of this episode, I'm going to take you through a hypothetical to show you how we change our concept to fit the data through time. It'll be a hypothetical, but it's modeled off of what I'm going through right now. So here is a section of a geologic map from professional paper 312 of the USGS, it's plate 2. And here I'm just showing you the red granites of the outcrops, and there's an inset showing you where Dickinson County is and how they thought the Dickinson group related to other rocks in the area. And today, that relationship has changed. This map, this old map, although it's still valid data because the data in the field hasn't changed much, we've just accumulated more. So you can still use this, but if you're going to use it for age relationships, it's off. You can't use it for that. So the stratigraphic column there on the right is no longer valid. Well, not as a whole. It's not totally invalid. It's just the relationships are not valid. And here we have an actual transit from the same publication. The map, I just really think this is cool and I like the way it looks. Like I said, it's from the same publication. I forget which plate it is. It's plate 10, and all this stuff is free online. All you got to do is go to just Google USGS Publications, click there and search, and you can type in make sure you spell it out, professional paper 310, and this will come up and you can look at it and download it if you want. There's a big misconception that scientists hoard data, but actually stuff like this has been available to the public since the internet has become popular. All right, so there's no excuse not to, you can't sit there and say the information's not there, because it is there. Okay, so now, as I said before, we think the Dickinson group is equivalent to the Menominee group, mostly based off that red porphyritic granite, the date on that. And if you go back to this slide here, this cross section, what you see is you can see, well, what's called there's, Dickinson group we have detrital zircons from, the PV pond complex we have a date for, and the red granite. The red granite gives us a minimum age for the calco clay and for the calco clay group. But what you can see here is that, and from my other slide that I showed you, the other detrital zircons, that we can better form age relationships. So now we think the Dickinson group, either in part or in its entirety, except for maybe the 6-mile amphibolite, is Proterozoic. It's Paleoproterozoic in age. Right? It's not Archean. We're still working out the exact stratigraphy of the Dickinson group and how it relates to other rocks, but we can say for sure, based on what present data we have, that it's not Archean. Dating methods are really refined now. So we're getting into better understanding of these sedimentary packages within the UP and how they relate to one another. And this does have practical use too, because if you can stratigraphically figure out how things relate to each other in cross-section and over large areas, you can actually do targeted drilling for minerals and other resources. So, all right, that's the end of that part. Now I'm going to show you a hypothetical one that'll kind of hopefully put this together for you. Okay, so I totally just made up a geologic map, all right here, because this is our hypothetical geologic map. This would be an actual map, a plan view. I did not put on here any scale because it's not really necessary for what I'm talking about, but if you're going to be a stickler, we'll say the width of this thing is 50 kilometers, all right? Whatever, it doesn't matter. And this is roughly modeled off of the kind of thrusting, fault, and stratigraphic relationships we see in the Upper Peninsula near Iron Mountain, but it's not an exact copy. I had to simplify it. And another thing I did for simplicity is there's no north arrow because it doesn't matter. I did not put strikes and dips on here because we're trying to get a big picture and I didn't want to restrict and make this more complicated than it needed to be. This here has an area of no outcrop, and I'm going to talk about why I had that on there later. There could be a stream or a river, a series of lakes and their glacial deposits that are covering that. And what you see, the big bold black line with the triangles, the teeth, that's a thrust fault. So the stuff in the upper left has been thrust over everything else on this map. Okay, so now say you go out in this area and it's a virgin area. No one's ever been out here before. Okay, and you start making a map and you see in the lower right here, this side, you map this area and we'll say you have a radiometric date, but it's not a very good one. So you have this granitic gneiss at 3.39 billion years. That's the GA, stands for billions of years ago. And you notice you have a diabasic conglomerate and an arkose set in her tongues with the conglomerate and a sandy limestone and a slate above that. Now this slate, you might say, well, you got a bunch of sedimentary rocks and a metamorphic rock. Well, the slate, I'm just calling the slate overall, it probably would have a shale facies away from the thrust fault, but you may not be able to recognize that. So you basically map up to the thrust fault, okay? And you sit there and you come up with some formations. You sit there and you call it, we'll just say for the sake of argument, we're not going to give it, you don't name groups and formations after, you don't just give them their lithology and give them letter groups. You don't do that, but I'm trying to keep this simple here. So we'll just say you call it B group. And there's your formations, your slate, your sandy limestone, your arkose conglomerate, your granite and granitic gneiss, all right? And your diabase, which you can tell cross-cuts the gneiss, and you don't really know how old it is, you just know it's younger because it's intruded into it. So you may not even name the diabase. You could, but you know it's not a part of that sedimentary package, and neither is the gneiss, okay? So later, maybe 10 years later, another geologist comes along, finishes the work you were doing in that area. And he maps, or she maps, the upper left hand, the part to the upper left of the thrust fault. And they notice that there's a granite, a protoquartzite, an andesite, an arkosic-wacke, a limestone, and a quartz arenite. And they're looking at this and they're like, okay, well, we mapped that. Well, we don't have any ages for anything over here, but that granite looks a lot like the granitic gneiss. Maybe they could be the same thing. The granite could just be the unmetamorphosed part of the gneiss, so they make the assumption that the granite and the gneiss are the same age. And that's fine. If they have no other information not to, that it would be the simplest explanation, that this is thrusted over some sort of syncline or something like that. And they start to think, they're like, well, my buddy did this work a decade or so ago, and he has a conglomerate. I don't have a conglomerate. Where there should be a conglomerate, I have a protoquartzite and an andesite. I have an arkosic-wacke, which is really close to the wacke, but not exactly the same. And then I have a limestone, which is not exactly the same as a sandy limestone, but they say they have some similarities. Say there are stromatolites in them or something. And on top I have a quartz aronite, but on the other side of the thrust fault I have a slate. So I start thinking, I'm like, well, I guess the sedimentary packages aren't related. Maybe that stuff that my buddy mapped 10 years ago is significantly older than the stuff I'm mapping right now. So I look at what my buddy did, and I have no reason to disagree with what his work was. So I make a group A, all right? And I say it's Paleoproterozoic because he said his group B was Archean, all right? So, I put nonconformity below the protoquartzite. I put my granite down with the granitic gneiss. So that's the only change. I've added that to the granitic gneiss. And then I have this second set of sedimentary rocks on top of my Archean sedimentary rocks. And this is kind of an analog to the Dickinson and Menominee. This is kind of the situation. The Dickinson would be B group and the Menominee would be A group. And then I noticed the diabase, we've learned a little bit more that this diabase is cross-cut everything in the area, so it's got to be the youngest unit. Okay, 25 years go by, a whole new generation of geologists come in. Radiometric dating, to trying to lock down these things, there's a push to find new minerals, so we need these dates. So, a brand new generation geologist goes out there and dates all this stuff, or as much as they can, all right? So what you're seeing here is a result of those dates. The numbers in black with the gray boxes are detrital zircons, so that's the oldest the formations can be. The granitic gneiss was dated, and it was close, but not quite at that older date. We have this purple with this white numbers. That's an overprint, an orogenic event, probably what formed that thrust fault. All right, so we have an overprint on a lot of the stuff. And we dated that granite in the upper left-hand corner, and it was nowhere, it's not related to the gneiss. It's significantly younger. As a matter of fact, it's almost 1 billion years younger. What, maybe 900 and some odd change million years younger? So what does all these numbers on here mean? Basically, these numbers mean our concept was wrong. We had the stratigraphic field relationships wrong. We got the basics down, like with the sedimentary rocks on the right hand side. We knew how that assemblage related to itself, but not so we knew how B group related to B group, but we didn't know how B group related to A group. And these dates, we got to figure this out. Well, what's wrong? Well, first, let's go back to, let's try to make a cross-section of our original concept. And say that just wasn't done for whatever reason, or it was done and it was done like this. It doesn't really matter. So we have our old conceptual cross-section, pre-orogeny. Both, I'm going to show you two cross-sections. They're both going to be pre-orogenic event, that pre-1.83 billion years ago. So you're not going to see the diabase on any of this, because that's after. All right. What you're seeing here is kind of the stratigraphy in the subsurfaces we would expect to see pre-orogenic thrust. Now, it makes sense. It's very simple. It's very layer cake. The only major problem with this is that you would have to erode a large amount of the slate to make room for group A. And if there was no basin forming event, and the slate's anomalously thick here, but you have no evidence that it's not. It could be that thick. So this cross-section, the old conceptual cross-section, for the information we had at the time, when we put B group as Archean and A group as Proterozoic, this is a logical cross-section, all right? If we were to go back 2 billion years ago, all right? What you're gonna see here is we've got this new data, now we've got problems, all right? So keep that cross-section in mind. So our old or a new stratigraphic concept, we need to define a stratigraphic column that fits the new data. And the biggest thing, what you're seeing here, is that granite is younger. That needs to be pushed up. You don't need to include it in group A, but it's definitely between group A and B. It's not below group B. And here you have a couple of things here showing the youngest zircons here are likely from that granite. All right, which would make sense because they're right by it. All right, so we've got us that old stratigraphic column is not working anymore. So in light of the new data, our original interpretation was incorrect. It has been falsified. And as every good scientific concept or model is, it's inherently falsifiable. A lot of times it stands up. This time it did not. It was falsified. Even though the interpretation was incorrect and hence our stratigraphic model was wrong, the basic concept still holds. We need to reevaluate our original model and come up with one that fits the new data. A more accurate and revised model has greater implications than just redefining the stratigraphy. It will help us better understand the tectonic history of the area so we can better understand the Precambrian overall. And like I said, it can help us look for resources. All right, so you're now that young geologist who got all these dates and you're like, man, this stratigraphy is messed up. What do I do? How do I fix it? Do I need to fix it? Well, it would help to have a working stratigraphic model so we can target our drilling, all right? So here's your new stratigraphic concept. The granitic gneiss doesn't change just the date, all right? Your granite is younger, all right? So it's over it, all right? Now what we do is we take our group A, okay? So we're gonna take the sedimentary package from group A and we're gonna put it on the left. And as you notice, we have removed the granite. We're not gonna include it in part of group A, which we probably shouldn't do anyway based on the age relationships. So, and we have our detrital dates and our actual dates. The detrital dates are gray background, the actual dates are solid black. So we put our formations there. That's our A group. Now we put our B group in based off the detrital zircons, and we notice that the slate and the quartz arenite are really close in their youngest zircons. It's quite possible they are related. Even though they are lithologically different, they might be chronostratigraphically equivalent. And I've talked about how we formally classify rocks in a previous episode. So this is how we start to develop our model. So we got our new model, we got our B group over there on the right. Now to finish our model, we're going to add the diabase because we have a firm date for that. So we just put it on top since it's the youngest. And that's what you do. The oldest goes on the bottom, you get progressively younger and you go up on the stratigraphic column. So this stratigraphic concept here is what we get, and I just threw the orogenic time frame with the overprints, those purple background ones with the white letters on there just for reference, although from a stratigraphic standpoint they aren't really that significant. So now in our new stratigraphic concept, we know that granitic gneiss is Paleoarchean. We notice that the Paleoproterozoic granite, now let me know it's not Archean. The two are separated by 0.912 billion years, almost a billion years, when before they were assumed based on field relationships to be the same age. And then we have our protoquartzite and our andesite, and then we have our sedimentary packages of group A and B above that. The andesite can be included in group A. There's no reason why it can't be. It's a lava flow. Now that we have this, and we know that it's all Paleoproterozoic except for the granitic gneiss and the diabase, can we refine this a little more? Can we make some new correlations? And the answer is yes. Based on the detrital zircons, the grays with the black numbers, the quartz aragonite likely correlates with the slate, even though they're lithologically different. The limestone with the sandy limestone, the arkosic wacky with the arkose. The conglomerate may or may not have an equivalent. That one's still up in the air, but it's definitely older than the arkose and probably younger than the andesites. So we just leave it in between the andesite and the arkose as a separate unit. All right. It may very well go intertongue with the andesite, but we don't have that part exposed, so we don't know, so we can't draw that conclusion. And then we have our protoquartzite at the very bottom of our sedimentary units, and then the oldest Paleoproterozoic we have is that granite. And our diabase is now known to be Mesoproterozoic. So we have all these dates, and in our stratigraphic concept, I've done this before. I did this with the Huronian group, the Menominee, the Marquette Range supergroup, just so we can get a better feeling of how these things relate to each other. And you're taking, remember, the detrital zircons, though the youngest ones, those gray background numbers, that just tells us how the maximum age of the sedimentary formation. It can be younger. Well, we do have brackets here. We have Mesoproterozoic diabase, and we have an orogenic event. And we have an andesite with an actual date in it and a granite with an actual date in it. And the granite is about 10 million years older than the andesite. So we can bracket it. So what we can do there, using and comparing to those detrital zircon dates, is we can estimate the time of deposition for all these sedimentary units. All right, so that's essentially what we've done here in the red. All right. Well, now we can take that data and those numbers, and we can generate a new cross-section, one that more fits the data. And just to show you real quick here, here's the old conceptual cross-section, pre-orogeny, and here's the new one. You look at this new one and you're like, that's all significantly different from the old one. Yes, it is. The thrust fault isn't on here because remember we're doing pre-thrusting, we're doing pre-orogeny. But if you look at it, at first you're like, it's a lot more complicated, but it's actually a lot simpler. You don't need to manipulate so many units. I mean, you look at it here and you see the arkosic wacky and the arkose, and those are really similar, so it makes sense that they correlate, that they're the same unit. All right, and now you know the granite intrudes the granitic gneiss and underlies the protoquartzite, so you've got that, and you got the conglomerate, and you have the sandy limestone, which is probably the exact same unit as the limestone. The quartz aragonite, based on those detrital zircons, is chronologically equivalent to the base of the slate. But lithologically, they're distinct, so they should stay different units. Okay, so now with that cross-section, we have a little dilemma. And that dilemma is, do we stratigraphically combine groups A and B, which group, in this case group B, would take precedence over a lot of the names in group A, or do we just leave them separate? And that's where we are right now with the Menominee and Dickinson. Remember, in lithostratigraphy it's lithology, that matters. It is not time. All right. So if we were going to redefine these units stratigraphically, we would need to consider some things. All right. Which formational names have precedence and which group name? Well, B group would end up being the name of the new group because it's older than A group. A group would be abandoned. And the granitic gneiss, the granite, those can stay their own units with their original names. The same thing with the protoquartzite and the andesite. There's no need to rename those. You just need to redefine their boundaries if you're going to do this, since in light of the new data. The conglomerate, no need. There's no equivalent unit that we're aware of. Okay? But then you get into the Arcosaguaci and the Arcos. Those are likely the same thing. Now, are they lithologically significant enough to remain two separate formations? That's a judgment call. My guess is no. So they should be put into one formation, and then the Arcos and the Arcosaguaci could be two separate members. Same thing with the limestone and sandy limestone. Now the quartz arenite and the slate are a little different. The quartz aranite is lithologically distinctly different from the slate, and although it's on the basal part of the slate, it doesn't seem to intertongue with it, so it could remain its own formation. So we would have to redefine all this according to the North American Stratigraphic Code. Or there's another option. Instead of doing that, we could simply just leave the groups as they are. Just make sure somebody writes a paper correcting the stratigraphic relationships, showing that new cross-section, but leave the names as they were and leave them as two separate groups. I would prefer to do the former than the latter, because in the long run, the latter, keeping everything with the same names, is going to cause confusion. All right, we have enough dates from the example I gave you to show that there is a close relationship between a lot of the units. So redefinition is warranted in this case, in my opinion, in my hypothetical opinion, and in my opinion, the Menominee group and Dickinson as well. But we aren't to that point with the Menominee and Dickinson groups yet. We still need to understand some more field relationships and get some more dates before we can do that. But I think this Geo-Files has been long enough. Anyway, if you have any questions or need me to elaborate, or if I wasn't coherent enough, which does happen, please leave questions below, comments below. And I think that's it. I hope you learned something.